Hello everyone. So in this video, we are going to understand how the DFS graph traversal algorithm works. So for this, we'll be solving three problems. The similar variation around the DFS, which will make clear how the basic core of the DFS basically works, how the DFS problem basically we can solve. So the very first problem will be the number of islands. The second will be the variation around the same, the maximum area on the island, and the third will be the number of enclave. So once we're able to solve these three variations, the core concept how the DFS graph traversal algorithm works will be pretty clear to us. So let's go ahead and solve the problem one by one. Yeah, so very first problem for us is the number of the islands. So it says the given problem given an m cross n 2D binary grid, which represent a map. One is the land and zero is the water, and our goal is to return the number of island from this particular grid. Now let's see if there is any constant around this. So it says an island is surrounded by the water. So island is nothing, but all the lands which are surrounded by the water and is formed by connecting the adjacent land horizontally or vertically. So what do we mean? If we're at any particular cell, the valid moves are either the horizontal or the vertical. So these are the two only valid moves. So let's say if I'm particular this cell, I can move either horizontal or vertical. I can't go and move, the direction. This diagonal move. This is invalid move for me. And since we have to return the number of island, so in this problem, let's say given input, this could be one of the island, this could be one of the island, and this could be one of the island. So that's why the solution is three. The same can be seen here as well. So in this given problem, we have the three islands. So let's try to see how we're going to solve this. So the solution would be pretty straightforward for us. We'll try to go and visit each cell one by one and see whether this is an island or not. To be an island, this particular cell, the moment we find any cell which has the value one, that is a silent, that is an island. Then we need to figure it out if that particular cell, if the value is one, whether this is there are any connecting land to this particular the cell or not. And to figure it out, we just have to move, in either the vertical or horizontal direction in the valid move and see if that is a land, then this is again, connected island for me. So now let's go and see how we're going to solve. So we'll start from here, the very first cell from here, and I can move into the four direction and we'll see if I have the valid move or not. So I can't go and move, outside my the grid, whatever the grid we have got. I cannot go and move to whatever the current row I'm there, I can't go and move to the previous row, the outside of this grid. Similarly, if I'm into the first column, I can't go and move to, outside of this grid. Again, another invalid move if, let's say, if I'm onto this particular grid, I can't go move outside here and here. These are again an invalid move. If I'm into this particular boundary, I can't go move here and here. These will be the invalid moves. Similarly, if I'm here, I can't go move here and here. So that I think pretty clear. So now let's go and see the problem. So if I'm particularly on this particular cell, I can go move into the right direction or bottom in any of the directions. So if I go and move right, I could again find land which is connected to me. So from here I can go move down, or right is invalid move for me. Similarly, this is invalid move. From here I can't go and move backward again because that cell has been already visited for me. The moment I'm visiting any cell, we have to mark this as a visited or not, whether we have visited this or not. So again, just to make the picture clear, if I'm coming and visiting this particular cell, I'll mark this particular cell as visited. And then I can go and move into any of the valid directions. So from here, again, I can go and move into this direction. This direction will be invalid for me because this is already visited for me. The moment I visit this, I'll mark this as visited. I can go and move into this particular direction, mark this as visited. So I have covered, one of the island for me. Similarly, I can go move all the cells. Since these are zeros, they are not island for me. If I come here, I can mark this again, one of the island. None of the islands connected, the lands. I don't have any lands here. Similarly, I'll go move each cell one by one. If I come here, mark this as a visited, move into the right direction, mark this as visited. So this will be an island. So answer will be three for me. So that's pretty straightforward solution for this. Let's go and see the solution, how we are going to solve the problem. Yeah. So first thing, if you see, we are going to iterate, through every cell, line number 9 and 10, if you see the highlighted. We are going to iterate through the every cell by nested loop, and we are looking for any cell which has the value as a 1. If the value is 1, that means that is kind of a one of the land. Then we'll increase our counter by 1, and then explore recursively via the DFS algorithm from that particular grid into the recursive manner. So for the DFS, how does this work? The very first thing we need to check the boundary condition, whether we are going outside the boundary or not. So if I went to the current cell, I have to check I'm going outside my boundary. Rho is less than 0. So rho is less than 0 basically means if I'm onto this particular cell, I'm going outside this. The first column, I'm going outside this, right? So that's what this represent. I'm not allowed to go outside my current row. I mean less than 0, greater than 0, and similarly outside my grid length as well for each and any row or column. And also if the current grid is the equals to the value is water, I'm not going to add that is not a land for me. So even that also I can just go and ignore that. Okay. Once we are done that, once we are completed that, then we know that the current cell, whichever the current cell I'm here, that is a land for me. So that particular cell I have to mark as a visited. So to mark as a visited, there can be multiple approach. One of the approach could be, can we go and update the existing cell or existing grid? So in this given problem, it has not been mentioned whether overriding grid is allowed or not. So we are going to just override the current grid. So I'm just going to go and update, mark this current cell as a visited. That means I'm just updating this value as a 0 as a water. So if it's a water, I mean, this particular value will return me in the future again for me, right? And then I'll go and move into all the 4 directions from current row to the next row, next column, previous column. I'll go and move into all the 4 directions. And that's how, the total number of count will be returned to me from this, for all the islands here. So that's just a recursive call. So in this given problem, the time and space time complexity will be big O of m cross n. For each cell, we are just visiting only once. And similarly, the space will be big O of n, m cross n, because of the recursive stack, which we are going to use for this recursive problem. Now let's go and move and see the second problem, the second variation, max area of the island. So what it says, this problem is again pretty similar. Given an m cross n grid, an island is a group of ones connected in the 4 direction, either horizontally or vertically. So our goal is to find an area of an island. So the area of an island is the number of cells which has the value in the one in that particular island. So we have to return the maximum area of an island into this particular grid. So let's say for this particular problem, if I'm particularly here, so this is one of the island and the area is 2. For this particular island, the area is 3. For this particular island, area would be 5. And for this island, again, the area would be 3. So maximum area is 5. So we are just going to return the 5. So again, we are going to solve this problem in the similar fashion. But the only catch would be, the moment we are figuring out any island, we just need to capture how many lands are here and then figure out whether the current area is the maximum greater than maximum area which we have already calculated or not, and then we'll just go and update our max area. That's the pretty thing we are just going to do here. So let's go and see the animation as well, maybe. So we are just going to calculating each area, and the moment we find the max area, we're just going to update the max area value. Problem again the similar way, but here what we are going to see, we are not going to override the existing grid. We are just creating a new visited matrix 2D grid, which you can say, and then iterate through each cell in the nested loop and see if the current grid value is 1 or not. And also we have not visited the current cell. If the current cell is the one and we have not visited, then we are going to compute our max area. So max area will be math.max, the current max area till the time which we have calculated, or we are just going to assume this DFS function is going to return us one of the area. So the maximum area of this DFS function or the previously whatever we have calculated. And the DFS will be again the same. The base condition is the same. If you're going outside the boundary, return it, or the current grid is value is the 0, then return it, or we have already visited the current cell. In that case also just return the value as a 0. If not, then mark the current cell as a visited and then return the value 1 plus in all the 4 direction, whatever the direction we are going to move in the next row, next column. Just add those value. If you find any land here, then add those value and return from this DFS function. which will be written here to calculate the max area. So yeah. So the same again, the problem, the time and space complexity is again big of m cross n for us. Now let's go and see the third problem, the number of enclaves. So this is again one of the variation. Let us see what the problem says. It says given an m cross n binary matrix, move consists of walking from one land cell to another adjacent four direction land cell, or walking off the boundary of the grid. So either if I'm at any particular cell, I can move to any cell which has the value as a one, or outside of the boundary of my grid. So either I can move outside my grid of the boundary, or if any cell has the value as a one itself, I can't go and move to any the water area. So now they're saying we have to return the number of land cell in the grid for which we cannot walk off the boundary of the grid any number of moves. So we have to provide the number of cells in this grid from where we cannot walk off the boundary of the grid. So what do we mean by this? Let's say if I'm this particular cell, right? Can I go and move outside of the boundary of the grid? Yes, from here I can definitely go and move outside. Similarly, if I'm staying here, I can go and move outside. What if I'm here? Again, if I'm here, I can go from here, and here I can move outside. Similarly, if I'm here, I can go from here, and this path I can follow, move outside. From here again, I can go and follow this path and move outside of this grid, right? But what if I'm at this particular grid? I don't have any way to move outside from the right side because this is a water. I can't go and move from the top. I can go left. From here again, things are locked because it's water. From here, I can go just down, but things are locked again, from here. Here I can go right, but again, things are locked. That means if I'm in any of these four cells, I cannot go and move outside of my boundary, either from the top, left, bottom, or right, any of the way. So we just need to return the number of cells in this particular, say, these four cell. If I'm on this particular cell, I can't go outside, in this grid boundary. So that's the answer we have to return. So now let's go and see how we are going to solve the problem. So the solution could be pretty similar. I mean, just the opposite way. The very first thing what we need to do, we have to know whether we are at the boundary cell or not, right? Because if you're at the boundary cell, we know that we can go and move outside the boundary for sure, right? So first, we're just going to highlight whether we are into the first row, last row, first column, or last column, right? If you are in any of these values, right, we know for sure that if you're here, you can definitely go and move outside. Similarly, if you're here, you can directly go and move outside as well. If any of these particular cell, the value was one, you can also go and move here from here, right? Similarly, from here to here. And then what we will do, the moment we find anyone on these boundary cell, again we'll follow the similar DFS algorithm and see is there any connected node who has the value as well. If those are the connected node who has the value one, definitely that means if I'm from here, I can go and move, from that particular boundary in the reverse way. So now here we are doing the opposite way to solve. Instead of figuring out from the current boundary whether I can move outside or not, we are doing a reverse way. Reverse way means if you are onto this any of the boundary, the first row, first column, or last row and last column, go and figure it out, mark all the visited cell, which you can just visit from these boundaries. And then in the second run, run the loop again in the second time and go and see if there are any cells which you have not visited, right? So in the very first algorithm, what we will do, very first run, we'll from the boundary nodes, we'll try to figure out how many cells are there which we can visit. So from here, I can visit all these cells. From here, I can visit all these cells, right? There are nothing from the first column or last column, so I'll just leave that. And the second run, what we'll do, we'll just go and see if the particular cell is visited or not and the land, right? So here, since this is a water, we can just ignore it. We'll come here and then here come. We'll see this has been already visited, so we can ignore this. Here we'll see this is not visited, so this is not visited, so our counter will be one. Here again, this is not visited, so counter would be two. Here not visited, so counter would be three. Here again not visited, so counter would be four, right? So four cells are not visited and these all are visited, right? So we can just ignore them as well. So that's pretty how we are going to solve this problem. So in the second phase, just go and mark all the cells as visited. First, identify the boundary. Maybe I'll just reset it. First, identify all the boundary cells, and then go and visit all the mark the cells, the connected node uh, which are connected to this boundary. Mark them as a visited, and in the last, just go and count all the cells which are not visited. That's the pretty simple way. So I can just run again this thing. This to see. First, we're just going to highlight all the boundary cells on the first row, first column, last column. Then go and mark all the cells from the boundary as a visited, which all you can go and visit it. And then in the second iteration, go and count the cells which have not been marked as visited. That's the pretty straight way to solve this problem. So now the problem solution should be pretty straightforward again. We're just going to scan and see, each cell one by one. And then we're checking whether we are onto the first row, first column, or last column. If you're onto any of them, then what we are going to see whether this current cell value is one or not. If the current cell value is one, then we are just going to run the DFS algorithm so that we can go and mark each cell as a visited. Now that's our goal. If we are into any of the boundary nodes, we are just going to see if that the value is a one. If the value is one, go and mark every cell, those cells as a visited, right? Or by the DFS algorithm. So the DFS algorithm, if you see the same thing, if you're going outside the boundary length or it's a zero, just return one. If not, the mark the current cell visited, and then, go and explore in all the four directions. So that's what we did. And once we are done with this, then in the second iteration, go and count again these, all the nodes one by one and see if any of the values one, then increase that counter and then return this counter. That's pretty straightforward what we have done here. So I think again it's clear, but I'll just run the animation one more time to see this. Just highlight all the boundary, mark all the cells from the boundary cells as visited, and then count the remaining non-visited nodes. That's it. Then time and space complexity again will be the big O of n cross n.